there is one more seminar.
Let's start me and
Then I will go and start there.
Hello, good morning. Joseph? Hello, Joseph?
Nobody is there.
I thought these two people at least I can see.
They have joined and they are not there.
Oh. Anyway, there is still some time.
There is 10 more minutes.
Yeah, 10 more minutes.
Hello, can you hear us?
Yes.
Good. Are there any questions? The last name, yes, parent. Last name. What is the name? Shanmugapriya. Okay. Satya himself has not come. This I can start as soon as they come. Okay, very good. இது என்னோட பிளாக் போர்டு இங்கே பெருசாக வரணுமே இல்லை then only I can also see. Yeah, good.
start.
Hello?
You can start.
Yeah, we can start, right? Just 2 more minutes to start. But before that, if anybody has got questions, they can ask me. I will start exactly at 10. 2 more minutes. Joseph, Satya has not come, right?
No, I am here. I am here.
Oh, Satya also has come. Good.
Hello, sir.
Hello?
Yes, sir. Satya sir is here, I think.
Yeah. Yeah. He said yes. Yeah. If there are no questions, I can start now.
Yeah.
Yeah. Today I have 2 lectures as usual, and this will be my last lectures in this course, because what I had intended to do, I am completing today. Namely, I have come up to the full standard model. So the first lecture today, which is lecture 17, will be completing the standard model description. We have essentially done everything. I have to put the things together. That's all. The next 18th lecture will be neutrino oscillations. So that's all I wanted to do in this course, and I have done that. If there are any questions, you can ask me. And she will put all the lectures in YouTube. So those of you who have missed any lecture can actually look at YouTube. You can tell your friends also. Those, I think some of your friends missed a large number of lectures, but they can certainly look at the lectures in YouTube, and they can ask me questions in email, over email. Okay? So let me start. The full standard model is obtained just by combining the full electroweak theory, which I have already written down, and the full QCD. I have to simply cannot add both of them because there will be double counting. If you look at the fermionic d mu psi bar d mu psi terms for the quarks and leptons, then they will be coming twice, both in the QCD part and the electroweak theory. So we have to write it suitably, and that's all I am doing. Otherwise, it is the same thing which we have already written down. So let me write down the full Lagrangian for the full standard model. First, the pure gauge field terms for the gluonic part, d mu, g mu, g nu I minus d nu, d mu I minus. Now I introduce a notation. Remember, standard model is based on SU3, color SU3, and left-handed SU2 cross a hypercharge U1. And the coupling constant for this we will call G3, this G2, and this as G1. So this is G3, F5JK, the structure constants for SU3, G mu, J, G nu K whole square. That is the
second,
yeah.
Second term is G mu I, right?
I'm sorry. Oh, this one. Oh, yeah. G mu I. Then for the W field, SU2 gauge fields, d mu, W nu A, I, J, K go over 1 to 8, whereas A, B, C go over 1 to 3. Oh, here also minus G2. Structure constant for SU2 is very simple, only the epsilon tensor comes, W mu B, W nu C whole square. Then the U1 thing which is simpler, only the curl, d mu B nu, d nu, B nu whole square, like the electromagnetic field Lagrange. Now, so these are the pure gauge field part. Now I come to the fermionic terms. First the quarks. I think I introduced this notation earlier also. Q1, Q2, Q3 are the 3 generations. So n goes over 1, 2, 3. The left-handed quarks form a doublet, and there are 3 doublets. Here we have to write the complete gauge covariant derivative d mu I G3 lambda I by 2 G mu I plus I. Now the QL has got interaction with the gluons, W bosons and the B boson. I G2 Pauli matrix tau A by 2 W mu A and I G1 by 6. The hypercharge value I think for this is 1 over 6. I gave you a table of the hypercharge when I worked out the electroweak theory. Please go back to that table. From that we have to pick up this. This actually this term came even in the electroweak part. Qn null. Then the right-handed things which are singlets. D mu. QCD part is still there. Both the right-handed and left-handed parts are triplets under SU3, color SU3. So they will have these couplings. I don't know whether I mentioned it earlier. All the quarks are treated as color triplets, namely fundamental representation of SU3. That is why they interact with the gluons and generate the strongly interacting hadrons, including proton and neutron. The right-handed parts don't have interaction with the SU2 part. Remember, because SU2 is left-handed. So there is no such term, but the hypercharge will be there. Hypercharge, again the number hypercharge. Hypercharge, remember Q is equal to I3, even now you can work out why. I defined this hypercharge without 2. So whether they are doublets or singlets, this will come. And then the Q we already know, so Y can be worked out. And since this is a singlet, I3 is equal to 0, so hypercharge is nothing but electric charge, which is 2 over 3. B mu U N R. And similarly for the down quark, bar again. Okay, as far as QCD is concerned, this also is a color triplet, and the electric charge is minus 1/3, and so it will be 1/3 G1. Hypercharge is same as electric charge for the U and D quarks. I mean the right-handed quarks. No, the full quarks, all the quarks. This is what D, N, R. Maybe I have to mention a point about the notation. Remember, this is a very condensed notation. Look at this Q. How many components does it have? First of all, each is a Dirac spinor. Actually, it is psi of Q, which we write simply omitting psi. Psi is common for everything. So that is it's a 4-component Dirac spinor, and it is a doublet. So 4 into 2, 8, and also it is a color triplet. So I have to put an index alpha. Alpha goes over 1 to 3, the color index. So 3 into 8, 20. There are 24 components in this. Please remember. Similarly here, of course, here it is not a doublet, maybe 12 here. So now when we write down a lambda matrix, the Gell-Mann lambda matrix, that will act only on the color quantum number. So I have to put a lambda I alpha beta, and here alpha, here beta, alpha and beta summed over the usual matrix rules. Correspondingly, for tau is a 2 by 2 matrix that will act only on the doublet structure. So again I have to put some index, I don't know what I should call, Mn, PQ, let us say. Tau A PQ will come between QNLP, the up component of this, and the up component, down component, up component, down component. That matrix operates on that space. Of course, this is here there is no matrix, so that means it's a unit matrix, 24-dimensional unit matrix. Here also unit matrix. Similar things you have to think of whenever I have the fermionic terms. One more point. Remember, this is a doublet, so it contains, sorry, Q bar I should have written. U bar NL comes, and here U bar NR comes. U bar NL and UNL, they will come, sandwiching this d mu. Here U bar NR and UNR come. When you add both, L and R will cancel. Remember, 1 minus gamma phi plus 1 plus gamma phi is 2, and then a half will be taken care of by the proper normalization which we use in defining the left-handed and right-handed. So this together with this will create that full kinetic energy term, namely U bar with U without that L and R. L and R go together. Similarly for every term, we have to keep that in mind. I think I counted wrongly. This is a 4-dimensional Dirac field and a color triplet and a doublet under SU2. So the total number of components in that column is only 9-dimensional column. Here 9-dimensional row. But when you multiply by matrix, the suitable indices have to be summed over, as I already explained. Okay. I have done with quarks, but let us go to the leptons. Leptons are similar. Again summed over. Leptons also 3 generations summed over. L, N R, bar, gamma mu, d mu. The leptons don't have QCD interactions at all because they don't have strong interaction. That is the difference between leptons and quarks. Otherwise, leptons and quarks are very parallel. But leptons are all singlets under the color SU3, so there is no gluonic interaction. Plus I G2 tau A by 2 W mu A. Again, for these leptons, whether it is up or down, lepton, both of them I think hypercharge is half or minus half. The signs you have to take care of, I think I have put them correctly. You can check using this formula where I put them correctly. LNL, that is the electronic doublets over, and the electronic singlets E bar NR, gamma mu, d mu, and these are singlets, so it has only the hypercharge interaction. I think hypercharge is -1 because electron is electric charge -1 and I3 is 0, so it is just -1. E1 B. So that's all the leptonic part. Next we come to the scalar field, which is what gives rise to the spontaneous symmetry breaking through Higgs mechanism. This is the same as what we had in the electroweak theory. You can look at it. So it's a doublet, phi is a doublet, so G2 coupling is there. I mean SU2 coupling is there. And it is hypercharged also by looking at this part is the same. I already explained when writing down the electroweak Lagrangian. So Actually, this the Hermitian conjugate of this multiplying that itself. The Hermitian conjugate will make this into a row vector, and this will be column vector. You multiply them together, and that I use this notation. So this is not because this is not a number. This is a column vector, and then converted to a row vector by taking Hermitian conjugate, and that is multiplied on the left with the column vector on the right, and that is this term, and then the potential. And then the Yukawa terms, namely the scalar field coupling with the fermions. And here in all these are diagonal in the generation space, but here it can be non-diagonal because that is allowed by all the symmetries. Yukawa coupling matrix for the up quarks Q bar ml into phi c. The charge conjugate phi c, remember, is equal to I tau 2 into phi star. That is the definition of phi c, charge conjugate. Think we have to make the charge conjugate, otherwise the hypercharge will not match. Just as this is, all these terms are invariant, they are all singlets under the full gauge group. They are all invariant. Then this is just these are just numbers. The Yukawa couplings are put as numbers, but it becomes a 3 by 3 matrix, another 3 by 3 matrix for the down quarks Q bar ml. Here phi can come, here phi c will come into dnr. And then one more, that will be the electron thing. This is the leptonic Yukawa coupling matrix L bar ml phi E nr plus Hermitian conjugate of this whole thing. So I have to put a plus Hermitian conjugate for all these terms, and then the bracket closes. That is all. And remember, there is no new R, because right-handed neutrino has been punished, because you can easily see that right-handed neutrino is a singlet under all these. So I did not include them in the kinetic energy term because I did not write that. And similarly here, the left-handed neutrino comes in the doublet structure, but there is no separate right-handed. That's all. This whole Lagrangian is invariant under SU3 cross SU3C cross SU2L cross U1 hypercharge Y. Although the full Lagrangian is invariant under SU3 cross SU2 cross U1, SU2 cross U1 is broken by the Higgs vacuum expectation value through the non-vanishing vacuum expectation value, and namely phi vacuum expectation value is simply 0 and a number. The downward part becomes this is zero charge thing. So vacuum exists because we choose the potential with a tachyonic mass term for in this Lagrangian, and so remember all that which we said earlier. This is not the minimum, this is the minimum, and so there is a vacuum expectation value phi 0, which is what will give masses to the W and Z bosons through the terms here, through the terms, I'm sorry, here. This term, where is phi? Oh, I'm sorry, I should have said here, this term. Remember, this contains W squared or B squared with phi squared, and once you put phi squared as phi 0 squared a number, then that has a quadratic term in the W squared and B squared, which are the mass terms, and we identify the suitable combinations and define the W plus W minus Z. So that is the Higgs mechanism, and because of that SU2L cross U1Y, because of this breaks. Finally, only one symmetry remains, that is the gauge invariance of quantum electrodynamics. That is also U1, but it is a different U1 based on electric charge. So actually the third component of this combines with this to give this Q, as is clear from this equation. Okay, so this is finally the Lagrange. Finally, in the solutions, only this U1Q survives. All these things. I'm sorry. It's actually you should say more correctly. SU3 color never gets broken. There is no Higgs mechanism there. Okay. That is the spontaneous symmetry breaking mechanism. And not only that, this gives masses to the quarks and leptons also through these terms, through the last line, through the Yokowa couplings. All this we have done. And this term, let us look at this, gives you lambda phi dagger phi whole square, which is the coupling of phi to itself, a fourth order coupling. And then if you look at the cross term, it is minus 2 phi 0 squared into phi dagger phi, and then there is a constant term which we can always ignore, phi 0 power 4 lambda phi 0 power 4, and then there is a lambda here also. The lambda multiplies all the terms here. Now look at this. This is a quadratic term for phi, that gives mass for the physical massive particle which survives. Remember, we discussed this many times, mass term for the Higgs. So basically it is lambda phi 0 squared apart from some number, numerical factor, mass term for the Higgs boson, and it is this part of the theory which was not checked. All the other things were experimentally checked with the 3 generations, but the Higgs boson was never discovered in all the high energy accelerators until they built this large hadron collider, and even after building it they had to search it for about almost 10 years. Finally they found it in 2012. Higgs discovered in 2012 with mass 125 GeV, and that verified all the parts of the Lagrangian. So that's all I think. Now I'll make some comments. There are some important comments to make here, important remarks. One, baryon number and lepton number conservation. Actually this is the most general Lagrangian, most general, the L which we have written down is the most general renormalizable this adjective is very important. Lagrangian invariant under SU3 cross SU2 cross U1 gauge symmetry. With the given fermions, namely the quarks and leptons, which we already know, and this extra field, scalar field, which we introduced for symmetry breaking. So everything else is obvious here, except what is renormalizability. Renormalizability means, of course, we are not discussing the renormalization theory. That will require another course. Renormalizability requires that Lagrangian has dimension 4. I have to explain this. The dimension of this Lagrangian is 4, and for that we have to count the dimension. By dimension I mean the mass dimension, taking mass to be one dimension. And remember, I already mentioned in the very first lecture, in the fundamental units, mass is the same as inverse of length and inverse of time. You have to count like that. Energy and momentum and mass are the same, because H cross and C are 1. In that, there is only one dimension, namely call it mass or length. We will choose it as mass. So if it has dimension 4, it has mass dimension 4. So let us count it. For counting it, maybe how do we proceed? Let us take this term. Remember, this has got two derivatives of space-time, which will be mass dimension 1, because it is inverse of length. Derivative means inverse of length. So mass dimension 1 and squares, so mass dimension 2, and phi squared is there 2. So this 2 plus 2 has to be 4. Lagrangian has to be 4. So phi, the scalar field, has dimension 4. Why the Lagrangian has to have dimension 4? Because it's a Lagrangian density. Remember, I write it as curly L. And Lagrangian itself is, you have to d cubed x you have to take, and then it becomes Lagrangian, which should have the same dimension as Hamiltonian. Remember, Lagrangian and Hamiltonian, you know how to form the Lagrangian from Hamiltonian or vice versa. And from that you can see that Lagrangian and Hamiltonian, which is the energy, should have the same dimension. Okay. So, so you can easily see that since L is L t cubed x, and this has got a dimension, length dimension 3, and minus 3 because it is length inverse of mass, and so this is the same dimension as the energy, and so it should have dimension 1. Energy is the same as mass, so this has to have 1, and so L has to have 4. D equal to 4. That is why I wrote this. Okay. And from that we could derive the dimension of phi. By similar arguments, you should be able to establish the dimension of the gauge field, for instance. Here fourth order comes. So every gauge field, gluonic field or W field or B should have dimension 1. G, I'm sorry, phi should have dimension 1. That is what we concluded. And G, W, B also have dimension 1. So all the bosonic fields have dimension 1. What about the fermionic field, whether it is quark or lepton? Let us call it psi. Again, you can do the counting in the same way. D mu has dimension 1, and this is q squared dimensionally, and the total has to be 4. So you can easily see that any psi field, namely quark or lepton, should have dimension 3 by 2. So, I have given the dimensions of all these, and if there is there is nothing else which comes, therefore G1, G2, G3 coupling constants are dimensionless, like electric charge. In the fundamental units, H cross equal to C equal to 1, fine structure constant is 1 over 137, just a number. Fine structure constant, if you put H cross equal to C equal to 1, is nothing but E squared. So, E is dimensionless, and G1, G2, G3 also are dimensionless. That is the way you should count. And if a mass term comes, it will have dimension 1, because it is like energy, and in fact our dimension is defined as the dimension of the mass. So, I have explained. Now, therefore, actually to be you can see consistency, all the terms here, each term will have dimension 4, so that Lagrangian density is the dimension 4. You can certainly write down higher order polynomials in the fields very easily, but any higher order polynomial will not have dimension 4, there will be higher dimensions. Any higher dimensional operator will spoil the renormalizability of the theory. A quantum field theory is renormalizable only if it has dimension 4 or less. In fact, the way we have constructed, since there is no explicit mass term itself is generated here, but finally, and for the fermionic fields also, so in the Dirac field, the Lagrangian, remember the mass term comes as psi bar psi into m, and this is 3 by 2 plus 3 by 2 plus 1, so it is 4. Okay, but here the mass here of course is generated through the Yukawa coupling term. Why should it be renormalizable? If it is not renormalizable, the theory has got infinities. Probability amplitude, which you calculate any probability amplitude, if you calculate in higher order, I have already mentioned it earlier, if there is a closed loop, when you sum over the intermediate particle momenta up to infinity, the whole thing becomes infinite. It does not make any sense, because every probability amplitude should be less than 1. So, that is the basic problem of quantum field theory. We are not solving that here, but in renormalizable theories, if the Lagrangian is dimension 4 or less, actually this m psi bar psi, which I wrote down here, I will not mention it. So, all the terms are dimension less than 4, and hence it is a renormalizable theory, and only renormalizable theories are proper quantum field theories to be used in high energy physics. Until the standard model was built, Fermi theory was the theory of weak interaction, and remember, Fermi theory is not renormalizable. What is Fermi theory? Fermi theory, remember, we have discussed it in the beginning when I talked about weak interactions in detail. It is a 4 fermion coupling, psi bar psi, well, let us write p bar n into E bar nu, that kind of thing. Remember, each is a psi field. So, 3 by 2, 3 by 2, 3 by 2, 3 by 2. So, how much is it? 4 into 3 by 2. So, dimension is 12. 6, is it? 6. These 4 fermion couplings, and it's 3 by 2 plus 3 by 2 plus 3 by 2 plus 3 by 2. So, this is the Fermi coupling. That is why the Fermi coupling GF itself has to have dimension, and we have to compensate for this dimension, because we want to add it to Lagrangian. Finally, the dimensions have to match, and remember GF we finally actually it is 10 power minus 5 divided by mp squared. That is why it has a dimension of 1 over mass squared, which we finally converted in electroweak theory as g squared, apart from sin squared theta and so on, and mw squared by allowing a W boson to propagate. This is dimensionless. So, everything matches. So, Fermi coupling is 1 over m squared, so d minus 2. So, it makes it formally d equal to 4. But as an operator, field theoretic operator, is dimension 6, and that is bad news for renormalizability. So, Fermi theory does not make sense. Fermi theory can be used only in the lowest order of perturbation theory. As soon as you make precise calculation by including loop corrections, it blows up, and the construction of the electroweak part of the standard model solves the problem. Renormalizable W boson theory. All that is old story. So we cannot add any higher order polynomials, and now you check. So we cannot write any more terms consistent with this principle. Since we cannot write any more terms, we can now derive some consequences of this Lagrangian. You find that there is B and L conserved. I cannot write here, right? So where do I write now?
B minus A theory is renormalizable.
V minus A only changes this gamma mu structure, right? Gamma mu into that does not change the dimensionality. V minus A theory put into Fermi's theory is not renormalizable. That V minus A coupling should be made to a W boson. Then only it is renormalizable. V minus A theory per se is again Fermi theory only the gamma structure is different. Fermi had only gamma mu, and V minus A theory has got one V gamma mu into 1 minus gamma phi. Okay. Now I want to draw some important conclusions from this Lagrangian. So I think I have to use, I have to rub off some part of it at least. So that is how B and L conservation comes. How does it come? In this Lagrangian, assign B equal to 1 over 3 for every quark field, quark or anti-quark field. And B equal to 0 for all others, leptons or H bosons or H fields. And you can check if you assign these, in all these terms B is conserved, Q bar, everything else is and here of course Q does not come. Basically it is Q bar or UU bar or DD bar, which conserves it is these three terms which you have to look at, because everything else, and here also Q bar Q. So B equal to the baryon number is conserved. Okay, quarks transform only into change only into quarks by the interactions. Quarks cannot change into leptons, for instance. That will violate baryon number conservation. But the theory does not allow it. Just the structure of SU3 cross SU2 cross U1, you cannot form a Q bar L term which is invariant under SU3. You just try. That is a good exercise for you. Try to violate B conservation by having a transition between quarks and leptons. You will find that you cannot form an invariance, because quarks are all SU3 triplets. That is the reason. And the leptons are all SU3 singlets. By combining SU3 triplet and SU3 singlet, you will get only SU3 triplet. You will not get invariant. So that is the basic reason. And also assign lepton number 1. When I say B equal to 1 over 3 for quark, automatically B equal to minus 1/3 for anti-quark, L equal to 1 for all leptons, and L equal to 0 for all others, for all other particles. Again, lepton number you can see is conserved because it is always L bar L, E bar E, and here also. So both these are conserved by the Lagrangian, and we did not try to do that. It automatically comes once we assign this under renormalizability criterion. Okay. Then B and L, if you assign this, such quantum number B and L are conserved. The very stability of the world, namely stability of proton, all atoms contain protons, and if proton had not been stable, the world as we see will not exist in this way. So baryon number conservation is very, and similarly lepton number conservation also are essential for the world as it is now, and that depends on this B and L conservation, but you see, and this conservation are accidental conservation laws. Every conservation law is based on a corresponding symmetry. I remind you of the Noether's theorem, which I mentioned briefly in the beginning. Accidental conservation laws, accidental symmetries. Accidental. We did not design a Lagrangian that way, but it turns out that way because of the other things, renormalizability and the SU3 cross SU2 cross U1. Because of that, these conservation laws come out, and the very stability depends on this accidental outcome in the standard model. There is no basic reason. SU3 cross U2 cross U1 is basic because whole Lagrangian is built on that. And also the fact that the given fermions, leptons and quarks, the way we have constructed, and the phi field. If you add any more fields, this will not be correct. So that is what happens. Any attempt to enlarge the standard model to supersymmetry or grand unification always involves adding more particles. Once you add more particles, then you find that B and L are no longer conserved. Proton will decay, and you have to make special to conserve the baryon number. That is why the grand unification models in general predict proton to decay, but we so arrange that proton at least lives for a long time. The present experimental limit of proton lifetime is proton lives for longer than 10 power 32 years, I think. You have to look at the particle data to see the correct limit, because they are still searching for proton decay. Sometime it will be found, because ultimately standard model will be incorporated in a bigger model, a supersymmetric model or a grand unified model. Number violation, so such a slow violation that I mean only one proton, the probability for one proton to decay is 10 power minus smaller than 10 power minus 32 per year. See, you may ask, how do you experimentally establish a lifetime which is a lifetime limit longer than 10 power minus 32 years, when the lifetime of the universe itself is only 10 billion years, 13 billion years. The reason is it is a probability. So by increasing the number of protons, monitor a huge tonnage of matter, that factor gets compensated. That is how bigger and bigger detectors are needed in order to improve the limit, and such efforts are going on. One day I am sure they will see it. Okay, that is one point.
So the proton decays, it will decay into a lepton.
Yeah, the decays, the simple decays which are possible are proton can go into a positron plus a gamma or pi 0, for instance, or a neutrino plus pi plus, or a neutrino plus k plus, and so on. According to some models of grand unification, it is this which is the preferred mode, but they are checking in all of them. See, proton decays, this process can take place. P plus E minus, maybe pi, say a few pi's or gammas. What is P plus pi minus? That is hydrogen atom. Hydrogen atom itself will just decay into pions or photons. Okay, that is the first thing, B and L conservation, which are accidental conservation laws. Second, I think now I have to rub off this thing. I will use this itself. Second point. So this dimensional counting is very important for establishing renormalizability. Second question is, the old SU2 with which we started our lectures, the isospin, and the SU3 symmetry, which helped in the classification of particles into octets and decimates and so on, and helped even to discover the quarks, also are accidental symmetries. So, although they helped very much in the early days of particle physics, they are no longer regarded as fundamental symmetries. They are also accidental. What is the reason for the old SU2 and SU3? Simply because you remember, in fact, all the quarks, U and D, occur in the same way. So, if you make a unitary transformation on the UD fields, the theory is invariant. The only thing it may break is the mass term, which will come from here, and the masses of U quark and masses of mu turns out to be about 4 MeV. This is experimental determination. MD is about 8 MeV. Why the proton comes out with such a large mass, 1000 MeV, I have already explained. That is because of the blue field. So, these are obtained from theory of strong interaction, deeper, some other consequences of strong interaction, chiral symmetry and so on. Lot of theory and phenomenology is used in order to derive this, because you cannot see U and D quarks separately. Okay, and similarly MS is about 30 MeV. All the other quarks, the masses are determined more directly, because the charmed quark, the psi boson, remember the psi particle, half of the mass of the psi is basically the C quark. Similarly for the B, and the top anyway does not form bound state, it decays by adding the energy and momentum of the decays of the T quark, and take the invariant mass from that, namely energy squared minus momentum squared. The sum of energy squared minus sum of mass momenta squared gives the so-called invariant mass of any number of particles which are produced in the decay of T, and that invariant mass, from that only the mass of top quark was determined to be 175 GeV. So, all those are more or less direct determinations, whereas these are all indirect determinations. But the point to be noted here is, on the scale of strong interaction, which is more like 1 GeV or more, these are all almost zero masses, and that is the reason for the SU2, SU3 symmetry. We can even put mu equal to md, and to a certain extent it is equal to ms also, on the scale of GeV physics. So, even the mass terms are symmetrical, and that is how SU2 is a better symmetry than SU3, because this equality is better. Here also it is different, but equality is better than this is 30 MeV. So, that is the origin of the SU2 and SU3 symmetry. So, the old SU2 and SU3 are relegated to again accidental symmetries. The fundamental symmetries of are the gauged SU3, or the gauged SU2L and SU3C, which act on the different components. Okay, I mean you know the structure. That is why I said this is 9 components and so on, and it acts in a different way. But nevertheless, it is useful to compare the old SU2 with the new SU2. The old SU2 being the strong interaction SU2. These are called nowadays classification symmetries, and these are the basic gauge symmetries. So, let us compare the SU2 doublet, which we already know. Comparison of old SU2 and the SU2L of standard model. Remember, U and D are doublets. Proton and that is how we started. Proton and neutron are doublets under the old SU2, and then when we went to quark model, U and D are doublets. Whereas all the new quarks C, S, T, B are singlets under the old SU2, and all leptons are singlets. Under old SU2, I simply call it old SU2. Whereas under the new SU2L, the left-handed parts of the UD doublet are the second generation CS left-handed, TB left-handed are doublets, and rest are singlets. All the R parts, right-handed parts are singlets. Here leptons, all leptons are singlets, but here leptons also are doublets. Again the left-handed part. Doublets. So that is the difference between the old SU2 and the new SU2. So one should not confuse the two. Old SU2 is still very useful. I-suspend symmetry is still very useful. In fact, in nuclear physics it is very important. Actually, SU2, when it was discovered by Heisenberg, they immediately applied to nuclear physics, and it became very useful in nuclear physics also. So that is all about standard model. If there is any question, you can ask me. Next, I want to discuss neutrino oscillations.
There are some experiments setting some lower limit on the mass of the photon.
Mass of the photon?
What is the intention of those experiments?
I don't see. You should ask Govindarajan, who is pursuing that. He gave even a colloquium yesterday. In fact, I could not attend it. He has been talking about it for a long time. See, as a purely empirical question, you can always ask, is photon mass really zero? If photon mass is really zero, then the Coulomb law is exact. But otherwise, the Coulomb law will get a small modification, and exponential minus mu r has to be multiplied by 1 over r. A Yukawa term will come, and the mu, the value of mu is presumed to be 0. But now how do we experimentally check? I mean, it is important to check these things experimentally. From that point of view, is a valid point. But I don't see any theoretical motivation. Because once you put a mass term, gauge invariance of electrodynamics goes for, charge conservation will go for. Because remember, mass term for photon means a quadratic term in the vector potential in the Lagrangian, and that will not be invariant under the gauge transformation, namely a mu going to a mu minus d mu of chi, an arbitrary function. That will be violated by any a squared term. Only the curl d mu nu minus d nu mu is invariant. So gauge invariance will go of what, which is one of the basic pillars of all of electrodynamics and quantum electrodynamics. So I don't see any sense in that, even asking theoretical question. But you can also always pursue it as a sport. That's all I will say. It's not an important question. But in olden days, even person like Schrodinger raised that question. That was much before we understood these things more. Okay. One thing I forgot to mention, I introduced the important concept of baryon number. The person who introduced that is Wigner, Eugene Wigner, the famous theoretical physicist. He invented the concept of baryon number to stabilize the proton. Otherwise, proton will decay through the modes which I already mentioned. That was much before the understanding of standard model. I mean, even before the standard model came, much before that. I think in early 50s or so, he introduced that concept. See, if baryon number is a fundamental symmetry, then it should be gauged. Nowadays, the basic philosophy in high energy physics is any fundamental symmetry has to be gauged. whereas all these symmetries which I have discussed, namely baryon number, lepton number, they are not gauged. If there is gauged, if baryon number is gauged, there should be a corresponding gauge field with 0 mass. If it is 0 mass, then there has to be a long range interaction which has not been seen. So, symmetry has to be broken in order to give mass through the Higgs mechanism. That means you have to invent a Higgs field and so on. Similar things have to be done for a lepton number also. So, some people are trying that. Maybe the baryon number gauge field is such a heavy mass that it has not been seen. Maybe it will be seen one day. So, such modifications of standard physics are always being done. Baryon number, lepton number, people do introduce gauge fields, but those gauge fields should pick up mass through gauge boson, and then you have to invent a suitable Higgs mechanism. Then you have to search for that Higgs. So, the story does not end there. So, for the moment we leave baryon number and lepton number is exact.
I have heard one interview recently
Yeah.
by Dirac.
Yeah.
I think this interview was given in late 80s
Uh-huh.
or early 80s,
Uh-huh.
something like that.
Uh-huh.
So where he was asked about the particle physics, what are development of theories in particle physics,
Uh-huh.
he makes a comment that this process of renormalizability
Yes.
theories
Yes.
is not the right way to look at it.
Yes. Yes.
It is some ad hoc way.
Yeah.
That he makes a comment.
Yeah. Yeah. I am aware of that.
There must be a better way to
Yeah, I am aware of that. The way even quantum electrodynamics was originally introduced by him, the way it got developed by Feynman, Schwinger, Tonaga, and Dyson, etc., the renormalizable quantum electrodynamics, he did not like, because we are handling infinities. That is why my answer to this is they are really not infinities. Remember, the electron giving rise to a photon, that coupling, we simply write the old ones. Even up to infinite energies which are used in the perturbation theory, in the intermediate, there is some infinite energy photon, infinite energy, infinite momentum photon is emitted. Even for that we use the same old thing which we know to be true only for low energies. Somewhere it may break down. At what energy it breaks down? Maybe after that the coupling is 0. That is called the cutoff. So, I will use a cutoff theory. Once you make cutoff in all the momentum integrals in the intermediate states, it becomes finite, but then it becomes cutoff dependent. So, I will interpret renormalizability as renormalizable theories as those theories in which we extract numbers which are independent of cutoff, and the theory allows you to do it. And the cutoff dependent part we absorb into the parameters of the theory like mass or coupling constant. That is the way I will introduce. I will not use the word infinity. Then Dirac's objection is taken care of, in my opinion. Okay, I will use a cutoff. So there has to be a cutoff, because the full theory is not this. For instance, gravity is not included. If you include gravity, the Planck length will come as a cutoff. For instance, if there is nothing else, Planck length itself will be a cutoff. Cutoff means beyond that we do not know, so we can put it 0. That is the cutoff theory. That is called the cutoff theory. Actually, in all renormalizable theory calculations, higher order calculations, they always use a cutoff. Okay, that is one thing. The other answer to Dirac is perhaps he is right. The quantum field theory is not the correct theory. It has to be replaced by string theory. In string theory, there are no infinities at all. That Planck length automatically comes in the theory and makes the theory finite. Everything comes out finite. That is another advantage of string theory over the so-called local quantum field theory. Okay. Any other question or comment? Otherwise, I will stop here and I come back after 15-20 minutes, and then we will take up Neutrino oscillations. That will be the last topic. Yeah, Dirac did not like many things in quantum field theory, the way the quantum field theory was being done, the way it is being done even now. For instance, the way it is being done is we separate the interaction as the interaction Lagrangian and develop perturbation theory in that, and to make it convenient, we use a thing called interaction picture, which you might students might have studied even in their ordinary quantum mechanics course. There are three pictures. The time development in quantum mechanics can be given in many ways, but three are very important. So called Schrodinger picture, in which time development occurs only through wave function, state vector. The operators are time independent. In the Heisenberg picture, all the operators are time dependent. And then there is the interaction picture, in which the Hamiltonian is separated into free part and the interaction part. And for the free part, everything goes like it is something in between. It goes like a Heisenberg picture, if you like, but then the interaction is treated perturbatively. So that is called the interaction picture. And in order to make fun of Dirac, many people call this the interaction Dirac picture, because it is Dirac who did not like this picture, in which everything was done. Every calculation was done in the so-called Dirac picture, which Dirac did not like. But in standard local quantum field theory, there is no way to do it. Infinities, in my opinion, can be answered by putting a cutoff and trying to extract those results which are independent of the cutoff. And that really gives a description of all the experimental phenomena, provided you use the experimental mass and experimentally determine mass and coupling constant for the theory. That is the way the whole quantum field theory works now. This may be a temporary stage. It may be ultimately replaced by string theory, because string theory includes gravity also automatically. That is why it is finite, because Planck length automatically comes there. Okay, so yeah, after 15-20 minutes. Okay. Are there any questions? If there are no questions, I will start. Is that okay, Joseph, Satya?
Yeah, please.
Okay. So, I am going to standard model more or less is over. Now, I am going to talk about neutrino oscillations. The importance of neutrino oscillations is that through neutrino oscillations, neutrinos were discovered to have masses, and that cannot be explained by standard model. So, that requires, that says that we have to go beyond standard model. So, that is the importance of neutrino oscillations. So, let me, why do neutrino oscillations occur? Because of this intergenerational mixing which occurs both in the quarks as well as leptonic sector. In the leptonic sector, I already mentioned this mixing occurs through a unitary matrix both in the quark and the leptonic sector. So, let me write down, these are called the flavor states. Alpha could be E flavor or mu flavor or tau flavor. It is a linear combination of the mass eigenstates. When we diagonalize the quadratic terms which come from the Higgs coupling after replacing the Higgs field by vacuum expectation value, those are the mass terms, but they are non-diagonal mass terms. So, when you diagonalize them, you get mass eigenstates, and the original states are linear combinations. So, it can be written I going over 1, 2, 3. These are the 3 mass eigenstates, and these are the flavor states. It is the flavor states which have simple interaction with the either the see when the electron is produced in beta decay, for instance, the electron is produced, and what is produced as a neutrino is not a mass eigenstate. It is this linear combination nu e, which is what we similarly when mu along with mu comes nu mu, and that is a linear combination of mass. So, they are superpositions of mass eigenstates. Now, these superpositions are important, it turns out, because although we call them mass eigenstate, those masses are so close from an experimental point of view, you can hardly distinguish them when you are in any reaction, and we are able to distinguish them only through these oscillations, because what will be produced is only a linear superposition, a coherent superposition of these states. This does not occur for any other particle. In the quark sector, it is very different. We can see distinctly the masses, because all the masses of the quarks are very different, and the charged leptons E mu tau masses are very different. But for the neutrinos, the masses are so close together, so finely separated, that the linear superpositions are what are produced in the experiment. That is where the neutrino oscillations occur. This same thing can be written in this form also, nu e column vector nu tau is a matrix U times the other column vector. U is a unitary matrix. In the quark sector, it is called the CKM matrix. I already mentioned it. Here it is called the PMNS matrix. P, again I forget who it is. It's an Italian and 3 Japanese, and this is Sakata, the same Sakata who started SU3 symmetry in particle physics. I think Minakata Nakagawa. P always escapes. He is an Italian and these are Japanese. Okay, unitary matrix mixes them. In this form, I wrote it in this form because if I want to inverse, to get the mass eigenstates in terms of the flavor states, you have to take inverse. And remember, U inverse is equal to U dagger because of this relation. So, using all these, so if you want to now write in this form, nu I is equal to U inverse, that is what we have found here, nu alpha and here I alpha. That is the way it should be written, and of course here it is alpha which is summed over. U inverse is nothing but U dagger, and hence this can also be written as U star. Hermitian conjugate means star and transpose. Remember, transpose means alpha, I alpha will become alpha. So that is algebra which you have to keep in mind in what I am going to do. And I need the these are states, but they are complex conjugates. Namely, these are the brackets in the Dirac notation, and if you ket notation, and if you take the bra, this will become Hermitian conjugate. Take the Hermitian conjugate of this nu alpha nu I and U star alpha I. Complex conjugate will come here, a bracket, here a bracket. This is correct. These things let us keep in mind. Now, now I am going to start Neutrino oscillation, how to derive the Neutrino oscillation probability. We will use fundamental units H cross and C equal to 1. And let us start with a state vector of a neutrino which we will call psi at t equal to 0, which for instance one particular flavor state, it may be nu e for instance, but more generally let us call it nu alpha, which is equal to u alpha I nu I. And the time development, so psi t can be easily obtained because each mass eigenstate has a well defined energy, and the time dependence of a state vector you may remember from quantum mechanics is exponential of minus I e t over h cross, but h cross I am putting 1. So this is equal to u alpha I e power minus I, the energy of the state. Mass eigenstates are also energy eigenstates. So if at a later time t positive, I want the probability amplitude for this to contain nu beta, some other flavor. I take the scalar product of this state vector with nu beta. I hope that elementary quantum mechanics you know. I am assuming that. So this is equal to that is why I needed this. So put beta alpha equal to beta there, you will get nu j u beta j, then this thing u alpha I and nu, let me write nu j here because these are numbers I can transpose, I can interchange the order. So nu beta nu I scalar product, I am sorry, not nu beta, nu I nu j. That is what I write is this psi beta I write as j nu j this nu beta can be written like this by using this equation. I change I to j and alpha to beta, then you get this. So that is how this comes. So I put that. So scalar product of nu j nu I times u beta j star into u alpha. So that is the probability amplitude for a state which started as nu alpha to become nu beta at a time t. So, probability for that is, now this itself is remember all the states have to be orthonormal. So, it is delta ij, it is normalized and they are orthogonal to each other. So, they are Kronecker delta, and so this thing is I becomes j, and so it is u beta I star u alpha I into, I forgot to write the exponential, minus I e I t here. I summed over. Here it is I and j both summed over. But the double summation becomes a single summation because of the Kronecker delta, and this is the result. So, this is the probability amplitude. So, probability can be calculated from that. In nu alpha to become nu beta probability, I will write like this, is just the complex conjugate of this multiplied by complex conjugate of this. So, again double summation will come. So, should not use I for the other thing, it will get entangled. So, one here the summation is I, and for the complex conjugate I use j. So, that is why both will come. So, beta I u alpha I u alpha j star u beta j into exponential of this and its complex conjugate with the j. So, exponential of minus I e I minus e j into t. So, that is the probability amplitude for one flavor to get converted into the other flavor. That is what Neutrino oscillation is, because the different eigenstates travel with different different phases. So, when you go to a later time, the phases will interfere and produce in addition, it may part of it may be nu alpha, but the other combinations come, that is all. Let us for simplicity consider as an example two generations. Let us say electron and mu generations. This is an example. In that case, U is nothing but, it is a unitary matrix, but that can be written as cos theta sin theta. Theta is called the mixing angle, minus sin theta cos theta. So, in this case everything can be written as simply nu is cos times nu 1. So, cos I will call C cos theta plus sin nu 2. This is very simple to work out, the two state system, minus S nu 1 plus C nu 2, and vice versa, nu 1 is equal to C nu 1 minus S nu S nu 1. This is it correct? No, I should have written here the nu E and this is nu, and S nu E plus C nu. I am sorry, this is nu 1, this is nu 2, the inverses of those. So, in this case you can see what is happening more easily, that is why I am doing this. Psi at t equal to 0 is equal to nu E, which is cos theta times nu 1 plus sin theta times nu 2, and psi at a later time cos theta nu 1 exponential of minus E1 t plus sin theta nu 2 exponential of minus IA2 t. But I want to convert nu1 and nu2 into nu e nu mu. For that I use these equations. So it becomes cos theta into cos theta nu e minus sin theta nu mu exponential of minus IE1t plus sin theta nu e plus cos theta nu mu e power minus I E2t. So let us combine the coefficients of nu e first, which is cos squared theta e power minus IE1t plus sin squared theta e power minus IE2t into nu e minus cos theta sin theta e power minus IE1t minus e power minus IA2t. So now we can work out the various probabilities. So you get the result. I don't know whether I have got everything correct. Factors of 2 and so on always trouble me. Anyway, this is cos theta sin theta exponential, and you know how cos theta sin theta are related to exponential. So you can easily see that from this you can get PEE Remember, this started with E, so that may be denoted by putting E here. We start with E, and then the probability amplitude for getting nu E is this. Probability amplitude for getting nu mu is this. Square it, you get the probability. So E to E, this is the E to E. Check these things. I am not sure about factors of half, 2, etc. Cos squared theta. Combining the exponentials, you can write them as cos also, cos E1 minus E2 into T, and the PE similarly is equal to, I am sure this can be simplified also. What have I written? This is 1, obviously this is wrong, because this is cos squared theta plus sin squared theta whole squared, so I do not know how I got that. So let me write down only P. Please check this. Just calculate the square of this. What will you get? Cos power 4 theta, sin power 4 theta. That is correct. And then 2 cos squared theta, sin squared. I am sorry, that is the mistake. No, this is correct. But the coefficient of this has this term. Okay, so it can be simplified. Okay, cos power 4 theta plus sin power 4 theta plus 2 sin squared cos squared theta times this time dependent factor, and so that is PEE, and PE mu will be square of this, which is simpler, cos squared theta sin squared theta into twice of sine squared E1 minus E2 into t divided by 2. That is what I have written, but you please check whether these factors are correct. So, check whether PE plus PE mu, it has to be 1, total probability has to be 1. Please check that. The way with the 2's and halves I have got, I do not get it right. This can be rewritten as, I have written it as sine squared 2 theta sine squared 2 theta into sine squared before that let me calculate this difference in energy. Difference in energy will depend on the difference in mass. So, let us remember this energy means the total energy of the particle including the rest mass energy. You have to use Einstein's energy momentum relation. Energy is equal to P squared C squared is 1 plus m squared C power 4. Okay. Normally what we do is we regard P squared small compared to m squared or non-relativistic thing, then you will get mc squared plus P squared over 2m, please remember that. Now I want to do the opposite. P is large, extremely relativistic, because the particles, the neutrinos which come out from reactions are of the order of MeV mass. It will turn out, that is what you will see, that the masses of the, although mass is not 0, the neutrino mass are very small, a fraction of an electron volt. Mass is always small compared to this. So, under that approximation, this is P plus m squared over 2p. But P is more or less E, so this plus higher order terms. So, I will rewrite this as, well, you can put it as P, but this P I will change into more or less same as E. So, this is the formula I will use in order to compute this difference. So, that is the way it is usually given. It is sine squared 2 theta, because sin cos theta sin theta is 2 cos theta sin theta is sin 2 theta is sin 2 theta. I think sin 2 theta is simply cos theta sin theta. So, how to take care of, you have to calculate it and verify what I have written. So, this quantity can be written, the argument the t dependent argument of the t dependent oscillatory term can be written as delta m squared into t. What is t? Time taken is the length of travel of the neutrino divided by the velocity of the neutrino, which is 1, because c equal to 1. So, t is the same as the length of travel. So, I will denote it always by this, and then that 2e becomes 4e because of this 2, I think. So, this is the way it is usually presented. So, this is the probability for conversion, and similarly this also can be written in terms of such things, and then check this is correct. Okay. So, that is 2 generation, but let us really go to the more general thing and now try to complete that calculation fully. So, that is what we need. If this is correct, then PEE is 1 minus that. Sin squared 2 theta sin squared delta m squared L divided by 4. Okay, so let us go to the general case, because we need at least 3 generations. Some more algebra is needed, because already we have calculated this thing, we have to square it, that is all. I mean, I have already calculated it, but this can be written in another form, that is what I want to do now. I thought I had that calculation somewhere. Yeah. Now which higher above? Some of these equations we need, but anyway, we can always come back to them. From one basic equation, you can get all the others. So I simply use that and turn it into another form. That's all. This thing is same as I and j both are summed over u beta I star u alpha I u beta j star beta j no star alpha j star. That exponential I want to write in terms of cos and sine. Cos the difference in energy, let me call it delta I, delta E. These are all elementary calculations. There is no quantum field theory needed. Now this I want to rewrite it as 1 minus 2 sine squared delta E I j t divided by 2. That is correct trigonometric formula. So we have got this 1. When you multiply 1 by this, then this can be simplified. But remember, you use a unitary metric, and hence it satisfies u dagger equal to 1. From that you can get these equations u I alpha dagger u alpha j sum over alpha with this intermediate multiplication equal to 1. But u dagger I alpha is u alpha I star. So this can be rewritten as u alpha I star u alpha j equal to 1. So using this, you can rewrite, first of all there is this 1, and so what am I going to write? This as I j summed over u beta I mod squared, see whether this is correct, I equal to j. Take the I equal to j part, this involves all I j, take the I equal to j part, and for the I equal to j part at least this is correct. What should I write here? No, I don't want to do that. Please cancel that. So let us keep it like this, and I have written, I have come up to this. Then with the 1, I can say this is delta alpha beta. Yeah, that is the point. Why? Because beta I star into beta I beta I always mess up these things. U star beta alpha beta I, U alpha I, U beta j alpha j, that is correct. And yeah, this is delta alpha beta. Because of the unitarity equation, this is delta alpha beta. I don't know whether I wrote it correctly. This is delta ij. That is, if you sum over alpha, then it is delta ij. If you sum over alpha, you can write it in another form. Then if you sum over the mass eigenstates I, then it will be delta alpha beta, and that form gives this. Because u dagger u also is 1, and that can be written as sum over I. Now the intermediate set summation is I, and it is u alpha I. Dagger u. Oh, I took this here. This came from u dagger u equal to 1. If you take u dagger, then intermediate state summation will be, so this will give u alpha I, u I beta dagger is equal to delta alpha beta. And u dagger I beta is the same as u beta I star. So that is what I want to use. That is what I have used here. U star beta I into u alpha I is delta alpha beta. So I have taken care of this term 1. That's all I have done. Then rest of it I have to be careful again. First let me write it down and then I will explain how I get it. So what I have done, I have simply taken this term, and that gives this. Now I have to take care of this term plus I have taken I not equal to j here, although all I j's are supposed to be there. If I is equal to j, it is equal to 0 because delta Eij is the difference in energy. So when I equal to j, it is 0. And that is why I equal to j need not be put. And then for this, again we have I not equal to j, only u beta I star, u alpha I, u beta j, u alpha j star into sine delta E I j 2 divided by no, 2. That's all. Now this thing I want to write it as minus 4 I greater than j, real part of u beta I star u alpha I u beta j into u alpha j star into same sine square delta E I j T by 2. Let me see how I get it. First of all, whether it is I greater than j or I smaller than j, it will contribute same way, because remember sine squared of that comes. So, because of that, the negative sign gets cancelled. So, if I write only I equal to greater than j, I have to multiply by 2. That's all this is. There is nothing else in that. But how do I get real part? How do I get only real part? The imaginary part should cancel, but I don't see it offhand how it cancels. Remember, all the U is a unitary matrix. Although in the 2 by 2 case it turns out to be a real matrix, in general it is a unitary matrix. In general they are complex. That is why I put real part. But the imaginary part of this has to be 0. How? Imaginary part is this minus its complex conjugate. So, it will come as bj u bj star u alpha j u b beta I u alpha j, and that should be the same, because this is again sine squared. So, it is the same. So, this minus its complex conjugate is 0. So, imaginary part is 0, that is all. So, only the real part contributes, and so I have written it as a real part. Now, this also has to be treated now. So, this is equal to again I greater than j u beta I star u alpha I u beta j u alpha j star sin delta E I j into t plus I greater than j only I have put. So, I smaller than j now I have to put separately. Otherwise, it is the same. Delta. Okay, that is this term within the circle. But this can be rewritten as minus I greater than j u beta I star u alpha I u beta I u alpha j star into sin squared delta I j t. Why? Namely, I see I and j are summed over. So, instead of I call it j in this I goes to j goes to I, in which case I has to be greater than j. So, this can be rewritten this way. What is the advantage of that? The advantage is, now if you add this to this, you can see it is just the imaginary part. Yeah. I have to add that to this. Let us call it I am adding this part, not this, because this and this are the same, but I am adding it in this form. Add this to this, and that is equal to minus 2 imaginary part of I greater than j u beta j star beta I star u alpha I u beta j u alpha j star into sin squared delta E I j into T. So, this plus this is this. So, now we have got all the terms I need. There is this, then there is a real part, there is an imaginary part. Real part comes with this coefficient time dependent term sin square delta E j T. What is the difference between the two? There is no by 2 here, I do not see. Yeah, there has to be a by 2. Whereas this is only sine, no square here, delta E j. Sorry, I am making so many mistakes. This also, there is no square. So, this is only sine term and that is sine squared. When it is sine squared, there is a divided by 2 in the argument. So, let us collect all the terms and write them down neatly. I have made so many mistakes and corrected them, so you have to be careful and write them properly. P alpha beta is this. Essentially, I am squaring this. You can do it perhaps at home more simply and then verify my mistakes, and correct my mistakes and verify what I am going to write down now. I am just rewriting this. So, P alpha beta, first of all, there is a Kronecker delta minus 4 I greater than j, real part of u beta I star u alpha I u beta j u alpha j star sin squared. Now, I can rewrite this delta Eij in terms of mass square difference. Remember that I had done that in the extreme relativistic limit, because all the neutrinos which we detect are extreme relativistic. So, delta m squared Ij, delta m squared by definition is mi squared minus mj squared into L over 2E, that is this term. This term rewritten as in this form, this term. Then there is one more term, that's all. One imaginary part comes and another real part. Twice of I larger than j, imaginary part of u beta I star u e. Again, I made another mistake maybe. The real part comes with sine squared and the 2e will become 4e, because in that formula which I derived it is m squared by 2e which comes, that other additional 2. So, this is a single power of sine. Again, yeah, since for sine it is only 2, for the sine squared only 1 over 2 came, because when we used the trigonometric formula another factor 2 came. So, this is the final result. Now, it is important to note the difference between this and this. Since this is square, it does not depend on the sign of delta m squared. This is called delta m squared. Whereas this is sine, so it depends on the sign. So, whether one neutrino is heavier than the other, that is called the hierarchy problem, which is not completely settled in the neutrino sector, and the INO, which is supposed to be a lab coming up in Madurai district near Madurai, will ultimately solve that problem, hopefully, if we ever come to do that. Okay. So, that is all the final result is P alpha beta. The important thing to note is it depends on the real taking the real and imaginary parts. So, the complex nature of U is very important. I am going to discuss that now. This PMNS matrix can be written in this way. Not only PMNS matrix, but even the CKM matrix will have the same form. Remember, it's a 3 by 3 unitary matrix, but first think of a 3 by 3 orthogonal matrix. 3 by 3 orthogonal matrix can be characterized by 3 angles, the Eulerian angles which define the 3-dimensional rotation. Remember, one axis of rotation, which will be determined by 2 angles, and then the amount of rotation. These are the 3 parameters. It can be written in terms of the Eulerian angles also. So, 3 angles. So, I have got 3 angles, and and using those 3 angles, I am now going to write down the trigonometric and trigonometric functions will come, cos theta and sin theta without. Just as in the 2 by 2, it's only a single angle, so cos theta and sin theta came. Here they will come in a more complicated form. So, I will write down C13, C12. C means cos. So, I introduce 3 angles, theta 12, theta 23, theta 31. So, this is rotation around the axis 3, this is rotation around the axis 2, this is a rotation around axis 2. So, cos or sine of those are written here. Then here it is C13, S12, and then here it is S13, minus C23, S12 minus S23. This rotation matrix you might have seen, for instance, when you discuss rigid body motion. I mean, Goldstein's book talks about them. Rigid body motion you might have done in classical mechanics. So, you would have studied this kind of matrices determined in terms of 3 angles. S13 or S31 are the same for me. So, let me call it S13. S13, S12. Here is S23, C13. The simplest way of deriving this is split this into 3 matrices. One matrix will have non-vanishing entries only here, the other matrix will have non-vanishing entries only here, and the third matrix will have non-vanishing entries only in the 1-3 sector, and each of them will be characterized by one angle. Multiply them out. So, U can be written in terms of 3 matrices in which only a 2 by 2 submatrix in each of them is non-vanishing, the others are simply 0, and use that. If you multiply them out, you will get this, that is all. But this is not complete, because we are not talking about orthogonal matrix, we are talking about unitary matrix. So, phases will come, and it turns out there is only one phase which comes, and that phase I call delta. and it comes only in some of these. So, this is the complete PMNS matrix or CKA matrix for that matter. Both matrices have the same form. Why only one phase comes? I am going to discuss that. That is very important. Not only that, this will be multiplied by another phase matrix which can be multiplied out. Let me call them a diagonal matrix E I alpha 1 0 0. So, this is a more general PMNS matrix e power I alpha 2. Two phases come here. So, that means there will be three phases, delta and alpha 1 and alpha 2. This delta is called the Dirac phase, alpha 1, alpha 2 are called the Majorana phases. I have already introduced the concept of Majorana neutrino. If neutrinos are Majorana particles, namely particle and antiparticles are the same, two extra phases come. I will derive that fact, both this fact, that if neutrinos are Majorana particles, two extra phases come. If they are Dirac particles, only one phase comes. But the point is, you can verify this statement at least. You just take this, write this in the Dirac form and then Majorana matrix, you will find that this alpha 1, alpha 2 never enter here. This is for Majorana case. So, alpha 1, alpha 2 are called Majorana phases. But in this, alpha 1, alpha 2 do not come. So, whether the neutrinos are Dirac or Majorana particles cannot be distinguished by doing experiment on oscillation, do not occur. So, something else is needed for that. Okay, so far it is fine. So, this counting of phase, why for the Dirac neutrino case only one phase comes and for the Majorana case three phases can come, I am now going to show you. It is a simple matter of counting the number of parameters in a unitary matrix. Yeah, I don't need any of this. Counting the number of phases. Remember, U is a unitary matrix. Let us take n flavors and n mass eigenstates instead of 3 more generally, because whatever we have done is valid for any number of flavors, is equal to is a n cross n unitary matrix. A unitary matrix can always be written as exponential of I times A, where A is a Hermitian matrix, A dagger A equal to A dagger is equal to A. Here it is unitary matrix, U dagger U is equal to 1. A is Hermitian, and a Hermitian matrix has n squared real parameters. This I did long ago when I talked about SUN, how many generators it has. It is n squared minus 1 because it has to be traceless also, because unitary unimodular matrix. Here no modularity comes, only unitarity, so n squared real parameter. How do you count? You can count it this way. First, let us look at the off diagonal elements. Number of off diagonal elements is total number of elements is n squared. We have to consider the real, when we say parameters, real parameters. So, out of that n, remember the diagonal elements of a Hermitian matrix are real, and I am putting here n squared for the off diagonal elements. That you can easily check, although it looks like 2n squared, but then because it is Hermitian, so the off diagonal elements are equal to each other, and then there are 2 parameters there. The 2 and 2 cancel, so it is n squared minus n off diagonal elements plus, then the diagonal element has to be added, so it is equal to n squared. So that is why n squared real parameters characterize the Hermitian matrix and hence characterize the unitary matrix. Now compare this with a real orthogonal matrix. Let us call it O. That also can be written exponential of A, but A now is an antisymmetric matrix, namely A transpose is the same as minus A. So how many parameters, how many real everything is real, is a real orthogonal parametric. So how many parameters are there are here? This also let us try to count. Again, take out the diagonal elements first, diagonal elements of this. Here only off diagonal elements have to be considered because diagonal elements are 0 because they are antisymmetric. Diagonal elements are 0. Number of off diagonal elements is n squared minus n divided by 2. So that is n into n minus 1 by 2. That is the number of parameters for an orthogonal matrix. For a 3 by 3 case, I said there should be 3 Eulerian angles. You can see n equal to 3, n equal to 2, 2 and 2 cancel, n equal to 3. And n equal to 1, I mean n equal to 2, n equal to 1 does not make any sense. N equal to 2, 2 and 2 will cancel, so it is 1, which is that cos theta, I mean single parameter which I used when I discussed it, the 2 by 2 problem. So the number of phases in U in general is equal to this n squared the total number of parameters minus what is required for an orthogonal matrix, which are only real numbers. This difference between this and this should be the number of phases. So n squared minus n into n minus 1. There is a 2 here. So this is equal to n squared plus n by 2. So this is the number of phases. But now we have to go back and ask what is really happening. U is sandwiched between the initial Dirac field, U or D, and the final Dirac field, 2 field operators which themselves are complex. They also have phases. And many times the phases which you introduce into the theory in a quantum field theory can be absorbed by the redefinition of the field, electron field or proton field, or quark field or whatever it is. And so only what cannot be removed by absorption into the quantum fields are genuine phases. So let us say there are 2n fields. For this n by n n flavor problem, the initial quarks and the final quarks, there are initially n quark fields, finally n quark fields. There are total number of fields are 2n. 2n fields have in general 2n phases. But since it comes as remember psi bar, psi sandwiching this u, that is how it comes, right? And so only the phase differences come into the final physical formula, only the phase differences. 2n fields have 2n differences, but only 2n minus 1 phases. No, I should say it differently. Only 2n minus 1 phase differences will come. See, we are talking about the charged current weak interaction. There only these matrices come. Remember, it's not the neutral current thing, but the charged current thing. Charged current operator involves 2n fields, but only the phase differences come. And remember, 2n fields will have 2n minus 1 if there are differences. It should be 2n minus 1, because if there are n objects in general, different n objects, and if you are concerned only with the differences between the n objects, there has to be only n minus 1 independent thing, right? The differences, if there are, for instance, when there are 2 objects, the difference is only 1. When there are 3 objects, the number of independent differences are only 2. So like that, I have to take out 1, and that is this minus 1, 2n minus 1 phase differences. So only 2n minus 1 phase differences can be used to absorb part of the n squared plus n by 2 phases contained in phases in U. So the number of significant, physically significant phases physically important phases, significant phases, is the differences of this with this. I mean, difference between this and this is equal to n squared plus n by 2 minus 2n minus 1. Therefore, it will become 2n plus 1. So this is equal to, we can easily check that this can be written as n into n minus 3 by 2 plus 1. So these are the, in an n by n problem, in an n Neutrino oscillation problem, the number of phases which can come in the U matrix, number of physically important, physically significant phases are only this. So you can see that for n equal to 2, what happens for n equal to 2? N equal to 2 is this and this cancel, this becomes minus 1, and they cancel, so there is no phase. That is why in the 2 by 2 matrix, I wrote without phase, only cos theta, sin theta, minus sin theta, cos theta. But for n equal to 3, this is not there, so 1 phase. And for n equal to 4 and so on, there will be more phases. So the important theorem is there have to be at least 3 neutrinos in order to generate at least a single phase. And now what is the importance of the phase? I have to mention here. The phase makes U complex, and U, remember, comes by, multiplied by fields, and then there will be a coupling constant also. It is the complex coupling constant which is a signal for CP violation. I am talking about CP violation now. CP violation is the same as T, time reversal violation, because of an important theorem in quantum field theory called CPT theorem. If you reverse the space, namely a parity operation, and if you reverse a time, and if you take from particle to antiparticle, that is C. So CPT transformation, all the 3 of them applied simultaneously, the theory has to be invariant. That's an important theorem in quantum field theory, which you can prove, which is given in books and so on. You can look at it. It's a very, proof is not very simple, it's a very complicated proof, but the theorem is valid. So because of that, CP violation is also the time reversal violation. And the signal for time reversal violation is complex coupling constant. And U also, as I mentioned just now, multiplies coupling constant, so it plays the role of coupling constant. So U becomes complex, namely phase, at least there is one phase, only if there are at least 3 neutrinos. So this important theorem was proved by Kobayashi and Moscow. I already mentioned it. Actually, they were concerned with quark. Whatever I did here is valid for quarks also. There have to be at least 3 generations of quarks before CP violation can be incorporated into the standard model. By that time, CP violation was known. I already mentioned that story when I discussed weak interactions. The CP violation was discovered by Cronin and Fitch in the K0 bar experiment, K0 experiment, K2 decay experiment. They showed that CP violation exists. K2 goes to some 2 pi mode, which is forbidden if CP is exact, and they showed that there is a very small CP violation. This was a pure experimental discovery, and by that time it was known because of Sakharov, who showed that the baryon number asymmetry, namely the whole universe is made up of only particles, no antiparticles. How can that happen? And one of the conditions which Sakharov formulated was that there has to be a CP violation. In addition to so many other there are 3 conditions. One of the conditions was there has to be CP violation in the theory. If standard model is the correct theory, then it has to have CP violation. The only way now known to introduce CP violation is through the CKM matrix in the quark sector. They were concerned with quark sector. So they predicted there have to be 3 generations. At that time, only UDS quarks were known. Only 1.5 generations were known. Subsequently, the 2nd generation was completed. The 3rd generation also was discovered, T and B. And the CP violation now is well checked in the B meson decay. Remember, B is a heavy, involves a heavy quark B quark, and many experiments, especially in Japan and also in US, confirmed the theory of Kobayashi and Moscow. So Kobayashi and Moscow got Nobel Prize for that, I think in the year maybe 2002 or something like that. So that is the story of the phases. But the story is not complete unless I mention one more thing. This is whatever I said is valid for the quarks completely, but for the neutrinos it is valid also, but with a suppose the neutrinos are Majorana particles, then there is a difference. This is for Dirac. For Dirac neutrinos. For Majorana neutrinos, we have to take care of the fact, remember Majorana neutrino, the particle is the same as antiparticle. So in some sense the Majorana neutrino field is a real field. It cannot take up any phase. And so for Majorana, so if there are n fields, only n phases therefore can be observed. Now it is not the difference of phase, but the phase itself. Only n phases can be observed. When we talk about, let us talk about the neutrinos and the charged leptons, which are coupled in the standard model through the charged current interaction, and only the charged current fields can absorb the fields. Majorana neutrino field cannot absorb, so there are only n fields. So the number of significant phases is equal to this number n squared plus n by 2 minus n, which is n into n minus 1 by 2. So for n equal to 3, you will get 2 and 2 cancel. So for n equal to 3 phases. One phase is already accounted for as the Dirac phase, the other 2 are called the Majorana phases. So that is the change. Okay, this they did not do, Kobayashi and Moscow did not do, because they were bothered about quarks, and at the quark, for the quarks there is no Majorana complication. We do not know 3. So these phases are CP-violating phases. There will be 3. That is why I had to add 2 more. And where will they be seen? They will be seen in the neutrino-less double beta decay. I think I did talk about it earlier. In the neutrino-less double beta decay, the Majorana nature of the neutrino comes explicit, and there the formula involves alpha 1, alpha 2 also. Your oscillations will not detect it. I am sorry, I am exceeding my time. Can I take 5 more minutes?
Yeah.
Just 5 more, so that I can complete it, because I don't want to come just for that. So I have to connect it to the experiment. So just give the experimental results. That's all. We have already discussed this, so it's only a repetition of what we already know. So it turns out that, so the results. What are the results? First of all, maybe I should mention in the quark sector, there is one phase that delta. So let me say quark sector. From all the experiments, the delta has been determined to be about 12 degree, I think. Please check it by looking at the particle data. For the neutrino sector, the story is more complicated, so let us write down all the results. I think I can remove some of these. Let me remove all this. Experimental results. Remember, the oscillation formulae depend on the distance traveled. If we are detecting solar neutrinos or atmospheric neutrinos, it will depend on the distance traveled between the sun and earth and so on, and the overall energy here and the mass square difference. And then the phases, the mixing angles, namely theta 1 to theta 2, 3, theta 3, 1, and the phase come here as coefficients of these oscillating terms. So all these have been determined by and large. Not everything has been determined by and large. So the mass square difference between 2 and 1 is about 7 into 10 power minus 5 electron volt square. Remember, electron volt square, that to 10 power minus 5. We know that the M2 is larger than M1, whereas here, see, there are only 2 independent, 3 objects, so only 2 independent differences. Only the magnitude is known to be 2 into 10 power minus 3 electron volt square. These are the most important results. The angles also have been determined. Theta 1, 2 has been determined to be about 30 degrees, and theta 2, 3 has been determined to be almost the maximal allowed angle, 45 degree, and theta 1, 3, which lay undetermined for a long time, now it has been determined to be about 9 degree. These are the experimental results. Delta is still not known, but now it is known that it is non-zero. So this is one of the important things to be determined. What is the other thing? The sign of this, that is called the, actually 1, 2 sector is called the solar sector, because this as well as this number was determined by studying solar neutrinos, solar sector. 2, 3 is called the atmospheric neutrino sector. And 1, 3 is called the reactor neutrino sector. And these data can be put in terms of a picture. This is M3 level and M2 and M1. Remember, there is a factor of 30 here. But we do not know whether this lies above this or below this, because only the modulus has been determined. So this is the other possibility. 2 and 1 may be here, and this may be 3. This is called the normal hierarchy, normal ordering. This is called the inverted ordering. Which is correct, we do not know now. No experiment has been able to determine it. Hopefully, if INO comes, one of the main aims of the INO experiment is to resolve this ambiguity in the masses. Some more results I can give from other experiments. So, see, the mass square differences are very small, but mass itself is not determined by this. That has to be determined by the conventional experiment. Study the electron energy distribution from a beta decay, for instance, tritium beta decay, which is supplied to the results so far, tritium beta decay. These are all oscillations, tritium beta decay. Tritium goes to helium 3 plus a positron, I think, positron or electron. So, the neutrino which comes there is a nu E, which is not a mass eigenstate, but a linear combination. And so, what is determined there should be regarded as this number U EI mod squared MI squared, and that number is less than, it used to be 2.2 electron volt for a long time. Now, I think it is known to be less than 1.5 electron volt. So, these are the masses, but they are below 1.5 electron volt. Compare it with the lightest mass particle known, electron, which is 0.5 MeV, million times smaller. One more thing, the double beta decay experiment, 0 nu, neutrino less, 0 nu double beta decay. There also it depends on the mass, but this is only if neutrinos are Majorana particles. Then only this so it's called double beta decay. And here it is a coherent superposition which comes. U EI squared MI, and then take mod. That is why this enters alpha 1, alpha 2. This will involve alpha 1, alpha 2, as well as the masses. This is less than 0.2 electron volt. This kind of double beta decay experiment has not been seen, only we have got upper limit. Whether the neutrinos are Majorana particles or not, or Dirac particles, we do not know. And in the INO K1, double beta decay, search for double beta decay experiment also will be mounted. I think that is all I have to say. So, this difference between this and this comes here, because this depends on sign, not sign squared. That is why the sign of the mass square difference is important. It comes here. Okay. Sorry, I exceeded my time, but if you have any question, you can ask me now. So, that is the end of this particular course of lectures, and they will all be put in YouTube soon by Gayatri, and she will inform us, and then maybe Satya, Joseph can inform the people who attended and people who did not attend, who had originally planned to attend. That was a large number, I remember. Many of them I am sure have dropped out, but since the whole thing is available, they can go back and look at it, and then send me questions by email. I will answer. That is the only way to learn. Okay?
Actually, it is, we have since recorded lectures.
Yeah.
I'm also thinking that sometime I will try to give, fill in some lectures.
Yeah. Oh, yeah.
Work out some details.
Yeah, yeah. That will be very nice if we can really fill in some details about Dirac equation and things like that.
Yeah.
That will go a long way in helping the students.
So I think we have 18 lectures.
Yeah.
And probably for each lecture I can think of doing some 3-4 lectures.
Oh yeah, that will be very nice. If you can do that, that will be very nice.
So thank you very much. It is really nice. I had attended all the lectures and I learned many things.
Very good.
Some of the things that appreciated better in these lectures are the importance of neutral current in development of development of standard model.
Yeah.
And of course, my ideas of spontaneous symmetry breaking and mass terms, Higgs mechanism have got much better in your lectures.
Thank you.
And also the experimental about the CP violation and asymptotic freedom. So I have, of course, I have to read more, but I think whatever I know, I have appreciated it much better.
Very good.
From this lecture. That is nice. Thank you very much. You have taken real interest to give these lectures. I'm very glad.
Thank you. Thank you.
That will be a great treasure, and I think we will use those lectures again and again.
Yeah.
For doing learning further research. Thank you, Rajat.
Thank you, Satya, and thank you, Joseph.
Joseph, you want to say?
Yeah. Yes, sir. Yes, sir. Yeah. So first of all, instantly I be thankful to Professor Rajshekhar and IMSC Media channel.
Yeah, IMSC readily agreed.
Put it in the YouTube.
Yeah.
And in fact, we were Satya sir and myself we were discussing about how to make Ajaj's whole half-century research work into physical form. Then somehow in this pandemic situation, Professor Rajshekhar is agreed to, even his health is not that much good, but he is so passionate. Every week he came to IMSC and taking 3 hours lecture in the age of 86. It's unimaginable. And each lecture is really a jewel of particle physics. And definitely, I really apologize that some of the lectures I could not able to attend because of my college schedule and some more things. But definitely, after this lecture, definitely I will go for again. And in fact, each and every lecture shows how much heartful effort that you put in learning subject. So really, I again thank Rajaji and India's help. Also, I thank Satya sir for taking the effort to bring in this entire ocean of knowledge in particle physics. And of course, I thank other people who helped with that. Thank you, sir. Thank you once again.
Thank you. Thank you. Thank you both. Okay. See you then.
Yes, sir. Thank you.
Yeah.
Thank you, sir.
Thank you, sir. Thank you.